let's talk about subspaces. The previous section dealt with vector spaces where we had to show 10 axioms uh, to be able to prove whether or not a set was a vector space. Here in this section, we only need to show just two of those, the two big ones, if you would say, and that is the closure with respect to vector addition and closure with respect to scalar multiplication. So the subspaces is pretty neat to look at. Not as much information to go through. Thank uh, uh, the Lord for that, right? And I did change the whole interface of the presentation from the with respect to the previous section. I was the previous section that I was doing the work in Word, and Word is crap, right? Especially when you want to do presentations, especially when you're writing and doing all the math. So we're gonna try PowerPoint. I think PowerPoint is for girls, but hey, if it works. So a little bit easier to kind of manipulate when you're doing presentations in PowerPoint. Hence the name for it. But anyway, let's get back to subspaces. So the definition, the theorem, and then we'll look at some problems. And the problems that I'm going over, especially for this class, are the problems for the homework. So you all should be really good to go in terms of being able to understand the homework. The quiz problems come from the homework problems. The test comes from the quiz. So I'm gonna go over everything in the homework, and that's gonna hopefully just answer every question, right? Well, there may be one or two out there, and that's fine. So the definition for a subspace: a subset W of a vector space V is called a subspace if of V if vector addition scalar multiplication holds true as defined on V. So the hard work is on V. So we assume that it's been taken for granted, and we accept that V has been proven to be a vector space. So if that's the case, then can we show a subset of V? Here, this subset, I get my spelling right. This subset, come back here, pen. W set to be written in this form, subset of V, can be shown that it's a subspace if the two properties of closure hold. So the theorem basically kind of says what the definition says, but the theorem then puts feet and legs and hands to the definition. So the definition is somewhat theoretical or in general, and then the theory is very specific. If W is a non-empty subset of V, so W has to have something in it. It cannot be the empty set. Then then W is said to be a subspace of V if and only if the two conditions hold true. That is, if U and V are vectors in W, then U plus V. The sum is also a vector in W. And then if K is a scalar and U is a vector, then K times U is also in the subset W. If these two hold true, then we say that W is a subspace. Let's look at this first one. Determine whether the subset of C, the space of all continuous functions on the set of all reals, is a subspace um, of this superset with the standard operations. What set? The set of all negative functions f of x less than 0. So here let f and g have the property. that f is less than 0 and g is less than 0 for all x that's real. So is it closed with respect to vector addition? What does that mean? I think if we talk about what it means and you understand that, then we're good to go for this entire section. And I tried to do a little talking back in the previous section for vector spaces, and if you got that, then it's the same thing here that's applied. That is, they're saying if you give me the whole set of negative functions, if you add negative functions, do you get a negative function? Yes. So if f and g are negative functions, then f plus g is also, we can say this, saying w is this particular subset. So here, then f plus g, that is also negative. Now the second one fails. So let k be a real number, a scalar, and f is in w. W is defined as the set of all negative functions. Then k times f may not necessarily be in the set. But k equal to -2. So -2 times f of x is positive or 0. So this set is not a subspace. Yeah, pretty cool, right? Determine whether here the same setup, the subset of space of continuous functions on the set of reals is the subspace. If with the standard operations, the set of all functions such that f of 0 is equal to 5. So here let f of 0 equal to 5 and g of 0 equal to 5. So first is f plus g at 0 is f of 0 plus g of 0. We get 5 plus 5, we get 10. Well, that means the sum is not of this type. So this is not equal to 5. So no. And then let k be any scalar. So then k times f is equal to k times 5 5k, but that's not equal to 5. So no, this set is not a subspace. What would make it a subspace? Um, it doesn't matter about this number here. What matters is this number there. So what would work if you had something like f of a equal to 0? So all the functions that map into 0. So when you start adding them, the sum is still 0. Take a scalar times that function, it's still 0. So this would work. Remember, the 0 always works, right? Here, the determine whether the subset of the space of all n by n matrices is a subspace of the space of all n by n square matrices with the standard operation of matrix addition and scalar multiplication, the set of all n by n lower triangular matrices. So what they're saying is that if you add any two given lower triangular matrices, would that sum be lower triangular? Yes. If you take a scalar, any scalar times a lower triangular matrix, will that scalar multiplication be lower triangular? Yes. So this subset is indeed a subspace. So let A and B be n by n lower triangular matrices. And let K be a scalar. So here the sum A plus B, and if we call this the subset W, then we say here if A and B are in W, so if A and B are in W, then A plus B is also in W. In words, all we're saying is that if I add two lower triangular matrices, their sum is also lower triangular. Geesh. Not responding is not okay. So if that be the case, then again K is, we set it up here in the intro, K is scalar, A is in W, then K times A is also in W. So W is a subspace of this big space. Here to determine whether the subset of M of the subset of matrices n by n matrices is a subspace of that particular space with the standard operations of matrix addition and scalar multiplication. The set of of all n by n matrices with integer entries. So let's say that this set is W. So we say let A and B be in W, and K is a scalar. So if I add two n by n matrices with integer entries, their sum would also have integer entries. Now, if K is real, A is in W, but K times A is not necessarily in W, since K can be any real number. So, say for example, take K to equal let's say 2/3, and the matrix A has entries 1, say 3, 0, and 6. So K times A would be 2/3, 2, 0, and 4. Now, these are good. Those three are integers. But uh-oh, 2/3 is not an integer. So this is not in W. This is not a matrix with all integer entries. Oh, that sky blue is kind of pretty. Oh boy. Okay, anyway. Thus, W is not a subspace. Hey, just one more problem and we're done. Not like the previous section, hour and I don't know, 30 minutes. My goodness. But I needed that time to kind of talk through where we had some technology glitches that kind of threw me off. Sorry about that. I could have edited all that out, but I didn't. I kind of just want you to see kind of what goes on, and A is just being real. Um, let's look at this last problem, and then we're done. Right? Catch some football. Determine whether the subset of the space of all n by n matrices is a subspace of the space of all n by n matrices with standard operations, matrix addition, and scalar multiplication. The set of all n by n invertible matrices. So what they're saying is that if you take the set of all, I forgot I gotta put some oil on this crazy chair. I'm sorry. Am I fat? Anyway, if we take the set of all invertible matrices of the same size, n by n, if you add them, is the result also still invertible? Not necessarily. And so the cool thing about proofs, mathematical proofs, is that to disprove something, you just use an example. Now you cannot use an example to prove a a generalized statement. We need to use the mathematical rigor to prove that. But to disprove something, you disprove by a counterexample. So let's call this the subset W. It's not a subspace. So let A and B be invertible n by n matrices. Let K be any real number. So if A and B are invertible, that's what that means, then A plus B may not be. Show by counterexample. Take A to equal to 1, 0, 0, 1. B to equal to negative 1, 0, 0, negative 1. Both are invertible because their determinants is equal to 0 because of the Monster Theorem. The Monster Theorem talks about um, how several statements in linear algebra are equivalent. If I have one that's true, then they're all true. So in that Monster Theorem, and I need to pull that back up and show that to you in one of these sections that is most important. It says that the matrix A can be reduced to the identity matrix. AX equal to 0 has the trivial solution. AX equal to B has the unique solution. Um, A is invertible. The determinant of A is not equal to 0. All these are equal uh, consequences. If one is true, then they're all true. This textbook calls that theorem the equivalence theorem. I just call it the Monster Theorem. Because back in the 70s when I grew up, we watched a lot of Godzilla, Megalon, Rodan, Gamera. It's a big, humongous turtle, right? Oh, the coolest thing. Right? And King Kong, blah, he was overrated. And it's like the foreign monsters. I don't know. They were just the coolest stuff, right? Um, King Caesar, that was good stuff. Um, and Gigan. Okay, I'm through. I was trying to think of Gigan, but you gotta have Gigan that comes and just breaks the sky. Man, you get a. Anyway, sorry. Let's get back to linear algebra. So, um, so that the determinant of A is 1. The determinant of B is 1. So here that means that they're also invertible. But A plus B is the 0 matrix. With determinant of A plus B is equal to 0. Well, the Monster Theorem says that if the determinant is not equal to 0, then the matrix is invertible. Thus, A plus B is not invertible. Thus, you conclude that W is not a subspace. Pretty cool. Now, if you want to see more problems um, for the students in this class, you can always go in Blackboard and look in where I've labeled old content, and you can pull up this section with the old textbook, and I go into probably more problems, but these problems are sufficient for now because the quiz and the test problems are coming directly from the homework batch that I'm going over. Okay, so hey, I hope you all are good with that. Take care.